Hello everyone, my name is Zhaowu Huang. It's my honor to make a presentation at ICPP. The title of my paper is Enabling Latency Sensitive DNN Inference via Joint Optimization of Model Surgery and Resource Allocation in Heterogeneous Age. My talk consists of 5 parts, including background, motivation, system model, solution, experiment, and summary. In recent years, an increasing number of DNN-driven artificial intelligence, spanning from autonomous driving to smart security, are emerging. These applications generate intensive data at the network edge and require mass computing resources to guarantee high accuracy and low latency. Currently, a widely adopted solution is to process such computation-intensive DNN inference tasks with edge computing. Such schemes treat DNN as a DAG or a train. At runtime, the end devices execute the part of the model and transmit the intermediate data to the edge server for further processing. However, the existing edge-based DNN processing methods still suffer from a set of limitations. First, the intensive intermediate data transferred to the edge incurs prohibitive network transmission latency. Second, unnecessary computing further imposes a heavy burden on the edge, increasing the response time. To address the above limitations, we explore a multi-exit DNN-based method to accelerate DNN inference. Due to the fact that low complexity samples could be classified in the earlier exit only with low-level features. The multi-exit DNNs are built by adding some extra exits to the original DNN. In this manner, each sample can ideally exit the network at the proper depth, avoiding layer-by-layer processing and saving inference time. Besides, some tasks could be early exit on the end device directly, avoiding the transmission overhead in edge computing environments. Each device equipped its MEDNN. Different end devices will choose different partition points and exit setting decisions. And the edge server will allocate corresponding resources to end devices. In the real edge computing environment, an edge server is shared by a variety of types of end devices with heterogeneous DNNs. Firstly, there are various end devices, such as Raspberry Pi, NVIDIA's Jetson Nano, and so on. The computational capabilities of different end devices are quite different. For example, the Nano, TX2, NX, and HX have different CUDA costs respectively. Secondly, there are various types of DNNs such as AlexNet, VGG, ResNet, Inception, and so on. Different DNNs have different characteristics. For example, AlexNet consists of 5 convolution layers and 3 connected layers. To achieve higher accuracy, VGG16 is trained to a deeper structure of 16 layers. To analyze the performance of MEDNNs in the edge, we conduct some experiments. In Figure 2A, B, and C, we study the effect of exit setting on performance by conducting experiments on the edge server. In Figure 2A, we can find that the number of exits is not the more the better in MEDNNs, because setting too many exits leading to a higher cost for exiting adjustment, and too few ones result in that the task cannot early exit at the appropriate depth. Figure 2B presents latency of all possible exit settings of ME AlexNet. The shaded bars represent the latency distribution of all exit setting combinations when the number of exits is given. The latency of different exit settings combinations changes drastically, although the number of exits is the same. The results of Figure 2C further demonstrate this feature. The latency of ME SqueezeNet changes drastically and irregularly, though the number of exits is fixed as 2, which leads to 2.185 times performance degradation in the worst case. As for model partition, the figure 2D indicates that the effect of model partition on performance. In this experiment, inference tasks are processed by an end device and the edge server, where the computing and the bandwidth resources are not shared with other devices. For optimal multi-exit ResNet 4034, the optimal multi-partition point is layer 9. Compared with the lowest latency, the performance degraded 2.85 times, showing the model partition significantly affects performance. In heterogeneous edge, the edge server and its network link is shared and competed by end devices. Figure 3 shows that the average performance degrades 4.62 times and 1.75 times in the worst case, compared with the optimal computing and network resource allocation. Improper allocation of resources can lead to even more prohibitive performance degradation. And in Figure 4, we gradually increase optimization items to explore the performance changes. The default setting for non-optimized variables are setting the model partition point before the first layer and allocating computing and bandwidth resources equally for all end devices. The result indicates that only optimizing one or a few of these four-dimensional variables is suboptimal, leading to up to 5.58 times performance degradation. Thus, it's necessary to jointly optimize these four-dimensional variables to deliver faster inference. From the above experiments, we observe that the performance is affected by the model partition, exit setting, and the computing and the network resource allocation simultaneously. Therefore, naively deploying MEDNs in edge still fails to deliver faster inference in the heterogeneous edge. How to deliver a faster DNN inference in the heterogeneous edge? We present an acceleration scheme for inference based on multi-exit DNNs with adaptive model surgery and resource allocation to solve the above problem, which involves jointly optimizing the model partition, exit setting, computing, and network resource allocation to minimize the task completion time. I will introduce the system model and the solution. This table shows the summary of key notations and the definitions. We first model the system as a mixed integer programming problem to minimize the task completion time of the whole system. This is the core idea of solution. We first transform problem P1 into a convex optimization problem by fixing the model surgery decision. By solving the problem P2, we can get an optimal resource allocation strategy, and then we substitute the strategy into problem P1 to get an integer programming problem that associates the model surgery variables. To solve the problem P3, we model it as a weighted conjunction game. Finally, we propose a decentralized algorithm to achieve a Nash equilibrium of it. Below, I will describe the solution in detail. The objective of each server and access point is to decide the best response to the decision profile of all end devices model surgery to minimize the task completion time of the whole system. Thus, the resource allocation problem can be formulated as P2 with two variables of resource allocations. In problem P2, the objective function is convex function and the domain is convex set. Therefore, the problem is convex optimization problem, and thus its optimal solution must satisfy the KKT condition. By solving the KKT condition, we can get the optimal computing and bandwidth resource allocation policy. According to the optimal resource allocation mentioned above, we can obtain the time cost of n devices I, which associates with the model partition and exit setting decisions of n devices. Therefore, we can overwrite the problem P1 into P3. The objective function of P3 is determined by integer variables, which is integer programming. To solve problem P3, we develop a game-based method. We first model the interaction between n devices as a weighted conjugation game with resource-dependent weights. The detailed proof process is presented in the theorem 1. Second, we prove the weighted conjugation game has a pure Nash equilibrium by proving the game is a exact potential game. After proving the existing Nash equilibrium, we propose a two-stage decentralized algorithm to achieve it. In the first stage, the end device I receives the current model surgery strategies of all other end devices from an edge server. Specifically, the edge server will collect the model surgery strategies from all end devices in the system and feedback the information to the end device which is making a model surgery decision. In the second stage, the end device I finds its best model surgery decision that incurs the lowest total time cost. The end devices I reports the model surgery decision to the edge server. Unfortunately, the model surgery, including the model partition and the exit setting combination strategy space of end device I is exponential. Each end device will take a prohibitive cost to select the best response to strategy profile. It's non-polynomial to search for the best response exhaustively in general. We can observe that the expected intermediate data size will be determined once the partition point is given. In this scheme, we assume that all end devices reasonably pursue minimize the FLOPS and the intermediate data size to save resources and the inference time. Based on the above analysis, we propose the theorem 3 to get an optimal exit setting with minimum FLOPS when given a model partition point. By this way, the best response of end device I to a strategy profile can be obtained only by searching all the possible model partition points, narrowing greatly the search space to ON and enabling efficiently to find a Nash equilibrium. We have derived the time complexity and the price of anarchy, and according to the time complexity and the price of anarchy, the system performance has guaranteed in polynomial time. To verify performance, we built a test bed that consists of the edge server and the heterogeneous end devices. For comparison, we have implemented the following mechanisms as benchmarks: IMA, spin, agent, IAO, and edge only. And IMA is the implementation of our method. We first verify the overall system performance. In this test case, we test the performance of our method in both homogeneous and heterogeneous environments of end devices and models. The experimental results show that the average speed up of IMA in figure 6, 7, and 8 are 2.29 times, 2.355 times, and 3.655 times less. We can conclude that the performance of IMA increases as the heterogeneity of the devices and models increase due to the joint optimization of variables. In the second test case, we explore effects of the four-dimensional optimization variables for average latency. We separately ignore one of the four variables to make four baselines. As shown in the figure 9, the results indicate that all these four-dimensional optimization variables affect the performance. In the third case, we explore the performance improvement and accuracy loss using multi-acid DNNs on the Raspberry Pi 4B. We can observe that the average speed up is 2.675 times with the average accuracy loss not exceeding 2%. Therefore, we can conclude that IMA achieves a significant improvement in inference speed with a smaller loss of accuracy. Finally, we conclude this paper. In this paper, we first comprehensively analyze and identify the key factors causing performance degradation. We propose IMA to minimize the task completion time, which involves jointly optimizing four-dimensional variables. To solve the problem, we decompose the problem into two sub-problems. We first obtain an optimal resource allocation policy with a given model surgery. And then we model the problem as a weighted congestion gain and prove the existence of the Nash equilibrium. We propose a decentralized algorithm to achieve a Nash equilibrium efficiently. We also derive the time complexity and the price of anarchy. The experimental results demonstrate that the proposed mechanism is efficient and can significantly improve the system performance, achieving up to 6 times speed up compared with the state-of-the-art methods. Thank you for listening.